Hi everyone, you're watching E635 Applied Linear Algebra. This is the 12th lecture. This is Debasattam, and this would be the first module. Now, so far what we've been looking at is starting from lecture number 11, that given a linear operator from a finite dimensional vector space V to itself, how can we break this linear operator apart and look at the smaller pieces, and we can look at how can we look at this operator from the uh, from the with tiniest details, right? And what we've realized is that the way to do it is to make it diagonal. We've seen that this diagonalization actually entails the fact that if we have a coupled system of differential equations given by dx dt equals ax or xk plus 1 equals axk, it's a difference equation version of the differential equation, namely dynamical systems, either continuous or discrete. Yeah, in that scenario, if you diagonalize this matrix A, which amounts to actually doing change of coordinates, a linear change of coordinates or linear change of variables, yeah, and diagonalize the matrix A, then this differential equation of the dynamical system becomes completely decoupled and you can solve it very easily. So that's the idea. Now, how can we diagonalize? We've seen that this linear operator on a finite dimensional vector space is diagonalizable if and only if it has as many linearly independent eigenvectors, yeah, as the dimension of the vector space V. It's an if and only if condition, right? Which is also equivalent to the following, that if I look at the characteristic polynomial of this linear operator, break it up into linear factors, like, so pull out all the eigenvalues together and write this down as x minus lambda to the power lambda 1 to the power k1 into x minus lambda 2 to the power k2 and so on up to s minus lambda r to the power kr, where lambda 1 up to lambda r, these are distinct eigenvalues. These numbers k1, k2 up to kr, they are the algebraic multiplicities, and the corresponding dimension of the eigenspaces of these corresponding to these eigenvalues, which are geometric multiplicities. If these numbers match for each and every eigenvalue, then and only then is the matrix diagonalizable. That is also we have seen. Yeah. Now the question that remains to be answered is that this is not always the case, right? Given a linear operator, there need not always be n linearly independent eigenvectors. Equivalently, the characteristic polynomial, I mean these eigenvalues, their geometric multiplicities need not necessarily be equal to their algebraic multiplicities. The question is, what do we do then? What can we do then? Yeah, so that is what we will see in this lecture. And in fact, the rest of this course, this is what we are going to analyze. This is the situation that we are going to analyze, right? So for that, I have to share my screen. Yeah, so we are in lecture number 12. So as I was saying, that there could be situations where the properties where there is a deficit in the number of linearly independent eigenvectors. One can look at very simple examples, like suppose I have this matrix A, which is 1 1 0 1, like this. Yeah, this matrix can be viewed as an operator from, say, R2 to R2. It's a linear operator. It takes a vector x and maps it to Ax, and suppose this is a matrix, right? How many linearly independent eigenvectors are there? First of all, I have to find out what the eigenvalues are. So I have to find out the characteristic polynomial, right? So let's try and find out the characteristic polynomial. That would be determinant of Si minus A, which in this case would be determinant of the matrix s minus 1 minus 1 0 s minus 1, right? And this determinant is of course s minus 1 the whole square. What are the roots? So this is my characteristic polynomial. Roots of chi is just 1. Yeah. In order to find out eigenvectors, what do I have to do? I have to solve for, so V is an eigenvector for eigenvector of the operator A corresponding to eigenvalue lambda equal to +1 if and only if AV is equal to lambda V, which means lambda times identity minus A into V ought to be 0, which is if and only if V belongs to the kernel of this operator lambda I minus A, right? In this case, what is my lambda I minus A? Lambda I minus A is going to be 1 into identity minus A, because 1 is the eigenvalue. That happens to be 1 0 0 1 minus 1 1 0 1, which is nothing but 0 minus 1 0 0, right? Yeah. Now, so how many linearly independent eigenvectors are there? So number of linearly independent eigenvectors, of course, corresponding to the eigenvalue 1, that is the only eigenvalue in this case. This number is the same as number of linearly independent eigenvectors, right? So number of linearly independent means that, so let me just write the equation and then it will be clear to you that this is nothing but the dimension of the kernel of lambda I minus A, right? Which is +1 times identity minus A. This dimension means that it's the size of the basis, which is the maximum number of linearly independent vectors in this kernel, and every vector in this kernel is an eigenvector corresponding to the eigenvalue 1. That is why the two are equal. Yeah. Now, if that is so, by rank nullity theorem, this must be the same as n, which is 2 minus rank of the matrix identity minus A. But identity minus A is this one, and that rank is of course 1. So this is 2 minus 1, which happens to be 1. So the number of linearly independent eigenvectors in this case is just 1. Thus, although it's a 2 by 2 matrix, it's so it has only one linearly independent eigenvector. Yeah. Of course, eigenvectors are many, infinitely many, in fact, in this case, because any multiple of an eigenvector is also an eigenvector. In this case, in fact, we can find out that eigenvector very easily. E1 is the eigenvector, is an eigenvector. E1 equals 1 0 is an eigenvector. But you can notice that is an eigenvector. But you can notice easily that any alpha times E1, which is alpha 0, this also is an eigenvector. But these are linearly dependent, right? These two. So in fact, it's an eigenvector only if it's in the kernel of this this I minus A, and the kernel is actually spanned by E1, right? So this, the collection of all the eigenvectors, which happens to be kernel of identity minus A, the set of all eigenvectors is equal to kernel I minus A, and this is equal to span of E1. Yeah, is that all right? And as we have seen, only one linearly independent eigenvector is there. However, the size, the dimension of the vector space is just 2. So size is 2, that is dimension is 2, but we needed 2 linearly independent eigenvector for diagonalization. But here we have only one linearly independent eigenvector. We can cook up such situations, more such situations. In fact, like for example, if we have 3 by 3 case, we may have something like 1 1 0 1 0 0 0 0 1. Yeah, this is a situation. Once again, it cannot be diagonalized. Here, eigenvalue. Once again, one can check that there is only one eigenvalue. The set of eigenvalues is just one, right? Dimension of the kernel of identity minus a in this case would be 2, yeah, which is less. This is the geometric multiplicity, whereas of course algebraic multiplicity of 1 is in fact 3. This is another example where it's not diagonalizable. We can also have something like, say, something like this. Yeah, in this case, once again, eigenvalue is just 1. However, dimension of kernel of identity minus a in this case is just 1. Yeah, which is equal to geometric multiplicity. However, algebraic multiplicity once again is 3. So once again, there's mismatch, so it's not diagonalizable. There are not enough eigenvectors. But these two situations are distinct because this has whereas this has 2 linearly independent eigenvectors. This is the dimension. This guy has only 1 linearly independent eigenvector. This is the dimension, right? In fact, here this in this case, kernel of identity minus a actually is spanned by E1 and E3. Whereas in this case, kernel of identity minus a is just span of E1 only, right? Yeah, is that all right? Yeah. Okay, now, okay then. However, you can easily see that, as we have seen in the last lecture also, that if we have all distinct eigenvalues, namely n distinct eigenvalues, then there will be n linearly independent eigenvectors. So a necessary condition for non-existence, non-diagonalizability is that there should be repeated eigenvalues. But it's not sufficient because even when there are repeated eigenvalues, there could still be n linearly independent eigenvectors, and it could still be diagonalizable, right? Okay. Now, the question that remains, as I have said before, that what to do in the situation when this is not diagonalizable, right? For that, what we need is, what we can do is, the next best thing is the next best situation is to block diagonalize. Yeah, maybe we cannot diagonalize it, but we can try to block diagonalize it. What do I mean by block diagonal? Look at this situation. This guy is a block diagonal matrix. This guy also is a block diagonal matrix. This also is a block diagonal matrix. What do I mean by this? This itself is this is diagonal. Yeah, there was a mistake here. This is 1, of course. Right? Look at this guy. This is block diagonal. This is one block and this is one block. Right? So what do we mean by a block diagonal matrix? Well, you see, if A is an operator, or maybe it's a matrix representation of a linear operator, and suppose it looks like some A1, then A2, and so on up to, let's say, AK. These are all 0 blocks of appropriate sizes. Yeah, like this, where these guys are square matrices. These I's are square matrices of some size, right? Then it's called a block diagonal matrix. So maybe it so happens that our linear operator may not be diagonalizable, but suppose we can make it. Can we? So we ask the question, in that situation when it's not diagonalizable, can we make it block diagonal instead? At least. The question is how. The answer comes via this observation of a special kind of a subspace, namely an invariant subspace. So here is the idea. So listen very carefully. This is going to be very important for us. Invariant subspaces. Right? What we mean by an invariant subspace. So here is the setting. Suppose A is a linear operator from V to itself. A linear operator. Of course, V is a finite dimensional vector space. This field, the field of scalars is given by scalar are coming from the field F. This is the setting, right? Now, let W be a subspace of V. Yeah, this subspace is said to be A invariant. You'll see that the name is actually very easy to understand, self-explanatory. A invariant if the following happens. For all vector W in the subspace capital W, we have A acting on W is once again a vector in W. Then W is called A invariant. Yeah. I hope you're getting what's happening here. Pictorially, well, suppose this is my vector space V, right? And within that, suppose there is a subspace W, right? Now, when A acts on it, A is a map from V to itself. The action of A on this subspace may take it to something different, no? Which we call A's action on W, right? Where will it be invariant? When will W be A invariant? If A's action on W produces a subspace which is contained in W. Meaning, when vectors in W get acted upon by A, they don't come out of that space W. They remain there. Perhaps it will be easier to understand if I give you some examples. Yeah. Think of this situation. Say we have, okay, let's first trivial examples. Yeah. Whenever we do something, first we start with trivial examples. Yeah. Of course, the zero subspace is A invariant for any A, doesn't matter, because 0 will always be mapped to 0. Secondly, V of course is A invariant because anything, you take any vector from V, make it act on, make A act on it, you get a vector which is also in V. So V is also. So the whole space and the zero space, both of them are A invariant trivially. Let me write that down also here. Mathematicians do like to use these terms trivially. Yeah. Now, non-trivial A invariant subspaces. Okay, so suppose I look at, so suppose V is such that V is non-zero and AV is equal to lambda V. Does it look familiar? Of course, that means V is an eigenvector. V is an eigenvector, right? Now, in this scenario, if you define W to be span of V, then you can notice that this is A invariant. Yeah, clearly, because you see, say suppose I take W in this subspace. What does that mean? It's in the span of V. So this means W must be equal to some alpha times V, where alpha is some scalar. That is how span in V looks like. No, any vector in the span of V looks like, right? Now, if A acts on W, that's going to be A acting on alpha V, but A is linear, so this is alpha AV, but AV satisfies lambda V, which is then this scalar times V, which of course is in the span, once again in the span of V. So I pick arbitrary vectors from the space W, make A act on them. I get vectors which are once again in the space W. So this is A invariant. So therefore, the span of any eigenvectors span of an eigenvector is A invariant. Yeah, not just that. In fact, if you notice, okay, we'll come to that soon. Next example, next non-trivial example would be, say, okay, look at kernel of A. Kernel of A is always A invariant. Although it could be trivial, kernel of A can be just the zero space if A is invertible. But even if it is not the trivial subspace, even if it's some non-trivial subspace, even then it's going to be A invariant. Indeed, why? Suppose V belongs to kernel of A. This implies AV is equal to 0, right? Which also is in the kernel of A, of course. Yeah, 0 vector always there in the kernel of A. Therefore, if V is in the kernel of A, AV is also in the kernel of A. Therefore, kernel of A satisfies this definition. But then there is more to it than just this. You see, kernel of lambda I minus A, if I take for any lambda, if lambda I minus A is not invertible, then is invertible, then it's just the zero space, which is A invariant. But suppose lambda is an eigenvalue and this is not zero, this is a little, this is more than zero, this contains non-zero vectors, let's say, still it's going to be A invariant. We can check. You see, suppose we have already seen, in fact, see, V suppose belongs to kernel of lambda I minus A. Yeah. Now, if I make A act on it, I get AV. Now, what can I say about AV? So let us look at lambda I minus A and make it act on AV. Let's see what happens. This is going to be lambda A into V minus A squared V. But notice that this is the same as, I can now pull out this A and lambda V minus AV. See what is happening? This is A into lambda I minus lambda times identity minus A into V. What has happened is the sequence in which I have written these two operators and the sequence in which I have written them here, the sequence has changed. Yeah, this is going to be crucial for us, that A actually commutes with lambda I minus A. It doesn't matter whether you make A act on the vector first and then lambda I minus A, or lambda I minus A first and then A. They commute. And because they commute, and I know that this part is 0, this is nothing but A acting on 0, which is 0. So you see, AV, this implies AV belongs to the kernel of lambda I minus A. Great, no? Because AV belongs to the kernel of A, yeah, AV belongs to the kernel of lambda I minus A. What this means is that kernel of lambda I minus A is A invariant. Compare this with before. Huh? Here I had said in part 3, I had said that, okay, look at the span of one eigenvector. That's A invariant. But not just that. Look at an eigenvalue and look at the space spanned by all eigenvectors corresponding to that eigenvalue, which is kernel of lambda I minus A. Right? Let me repeat. Kernel of lambda I minus A contains all eigenvectors, yeah, corresponding to the eigenvalue lambda, right, which is the same as the span of all linearly independent eigenvectors corresponding to a single eigenvalue lambda. So this space is going to be important for us, immensely important for us. So kernel of lambda I minus A. So that kernel of lambda I minus A, that whole space, whole subspace, which is kernel of lambda I minus A, that itself is A invariant. Yeah. Yeah, is that all right? With a little bit of effort, we'll also be able to figure out the fact that the following is also true. This is only a special kind. In fact, so suppose if S is a polynomial, the symbol for denoting a polynomial is this. What does this mean? This means that if S is of this form, it's a typical polynomial. It looks like A0 plus A1S plus dot 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 up to, let's say, A R is to the power R. Here's a typical polynomial where these numbers AI, they come from F, from the field. S is some variable. Yeah. These guys are called coefficients. R is defined to be the degree of this polynomial F if AR is not equal to 0. Okay. And AR is also called the highest degree coefficient. Okay. Now, it makes ample sense to look at FA, a polynomial operator. What does this mean? This is by definition I0 times identity plus A1 times A plus dot 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 up to AR times A to the power R, where A is an operator. And the square and various powers of the operator is easily understood. A square is A operated twice, A cube is A operated thrice, and so on. Yeah, I mean, just let me write this, that A square acting on a vector V means A V. This is just composition of maps. That means here I'm composing the same map with itself, a linear operator. Matrix wise is just a product of matrices, various powers of matrices. Okay, now okay, so for such a polynomial operator, note that kernel of FA is A invariant. Indeed, we have seen two special cases of that, namely when if A is just A, then kernel of A is indeed A invariant. We have also seen when if A is lambda I minus A. Yeah. So what is the polynomial corresponding to that? Lambda minus s. Polynomial is lambda minus s. The corresponding polynomial operator is lambda I minus a, and kernel of lambda I minus a is indeed a invariant. But not just that, for any polynomial it's going to be a invariant. Why? So let's say v belongs to kernel of fa. This implies fa, in fact this is if and only if fa times acting on v is 0. Now, so if I have av and make fa act on av, what will that be? Notice that this is the same as a fav. This is very crucial, that a always commutes with its polynomial. A commutes with any polynomial. This is not always this, this commutation of operators is not always true. It's very crucial to notice that this commutation will always happen. Two arbitrary linear operators acting on the same vector space need not always commute. But I mean, we may think that commutation doesn't happen because of the dimensions may not match. No, not like that. Even when look at square matrices of the same size, n by n square matrices, do they commute always? No, not necessarily. Right? So they need not commute always, but here they do commute. And because they commute and fav is 0, this is a acting on 0, which is 0 again, which then means, of course, that av also belongs to kernel of fa. So kernel of fa in that case turns out to be a invariant. That's what we wanted to show. Right? Here goes a homework to you. Show that image of fa are also a invariant subspaces. Check this. That is your homework. Yeah? Is that all right? Now, okay, good. But what then? What happens when I have, so I hope that you do understand what a invariant subspaces, what do a invariant subspaces mean? But how does it help us? How does it help us in getting that block diagonal representation of a linear operator, as I've been indicating? How does it help? The help comes in this form, right? Suppose let W, a subspace of V, be a invariant. Yeah. So if it is a invariant, well, because it's a subspace W, we can have a basis for W. So let B be a basis for W. Now I can extend this basis, by adding vectors. Yeah, again and again, as we have seen the extension. So that essentially means that there exists a subspace W prime such that V is equal to W direct sum W prime. This W prime is called the complement, not necessarily orthogonal because V need not be an inner product space, but it's some complement, yeah, of W, complementary subspace of W, right? And let's say B prime is a basis for W prime. We have assumed that W is a invariant, right? So now this extension of basis is nothing but that this means this B union B prime, this set must be a basis then for the whole space. must be a basis for all of V. This is nothing but extension of B, right? I have done some arbitrary extension of B to a basis for the whole space B. This is something that we have been seeing from the very beginning, right? But this is something that we can do. Okay. Now, as we have been looking at linear operators, so once again, let's look at this linear operator. Let us look at the representation of this A under this basis. Right? If we are dealing with tuples, if you feel more comfortable with tuples and matrices, then what we are doing here is that, so let me put it in bracket. Let me put it in different color. This is the same as we are trying. So B is, so B is, let's say, some vectors v1 up to v k, and B prime is equal to vector v k plus 1 up to v n, right? Then I define T to be equal to v1 dot 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 v k plus 1 dot 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 v n. This is my T matrix. Then what I'm trying to find is T inverse AT. What T inverse AT, how it is going to look like. Operator form, this is what we are trying to find out. How is it going to look like? Yeah. Now, this is absolutely crucial. You have to pay utmost attention to what I'm saying now. Okay. What is the first column of this matrix? What is my basis? Basis is like this, v1 up to vk and then vk plus 1 up to vn. Remember that v1 up to vk, the span of these vectors spans w, which is A invariant. Yeah. Now recall how the matrix representation of a linear operator is done. The first column is, okay, make A act on v1 and represent that vector in terms of the basis. So this is going to be A acting on v1 and its representation under this basis B union B prime. The second column would be A v2 B B prime, and so on. That is how it will continue up to A vn and its representation in the basis. Right? Now, notice A v1 is a vector, right? So A v1 is a vector. V1 is a vector from W, which is A invariant. So A v1 must be a vector in W. This is also a vector in W, which is nothing but the span of v1 up to vn, v1 up to vk, the first k vectors, k being the dimension of W, of course. I hope you understand that. So then, if I now look at this A's representation in this basis, the first column will have possibly non-zero entries only for the first k entries. The rest of them will be zero because these will correspond to coefficients for the linear combination involving k plus 1 up to k up to n, vk plus 1 up to vn. Those vectors are not required because it's in the span of this itself, right? And the same is going to be true for AV2, only up to k. Yeah, so these are only k, only up to k, and the rest will be 0. And this same trend will continue till the, how many? Till k columns, that is v1 up to vk, and these will be zeros. Then here may be something, because now I'm going to make A act on vk plus 1, and it may require all possible, the linear combination. So A vk plus 1 written as a linear combination of v1 up to vn may require all coefficients to be non-zero. I don't know. So all of this is unknown. Some entries will be there, I don't know. But what I know for sure is that this part is going to be 0. So what then means, what we mean by this thought process through which we have gone is that this now will admit a representation which looks like A11, which is going to be a square k by k matrix, some A12 whose size is going to be n minus k by n minus k, and then there will be an A22 which is n minus k by n minus k, and this part will be 0 of size n minus k times k. This is the shape, this is the structure of A in this new basis. If you are dealing with matrices, then the T that we have formed here, this T inverse AT will A nu, and this will be the form of, now let me write it in green color. Yeah, this is how A nu is going to look like. Yeah, I hope you understand what's going on. Right now, here is the $1,000,000 question. So how did we get this? Because because W was A invariant. Tell me what will happen if W prime is also invariant. So if W and W prime both are A invariant subspaces, then A in this new basis B union B prime is going to look like, of course, A110 will continue when A acts on vectors from B, its action on B, on vectors in B, gives us vectors which are in the linear combinations of vectors only in B. We don't need anything from B prime, right? Now, likewise, when you make A act on vectors from B prime, yeah, the action of A on vectors in B prime gives us vectors which are linear combinations of vectors only in B prime. They don't require vectors from B. Therefore, this part will then be 0, and we'll have A22 here. This is a block diagonal matrix. So this is the idea. So what we need is, so for block diagonalization, for block diagonalization, we need W prime both A invariant such that V is equal to W direct sum W prime. And then in the new basis involving basis vectors from W and basis vectors from W prime, in the new basis, the operator is going to look like a block diagonal matrix. What size? This size will be K by K. This is K by K, where K is the dimension of W. This is N minus K by N minus K, where dimension W is equal to K. I hope you're understanding what's going on. With a little stretch of imagination, if instead we have, for the general case, if further we can do the following, that V is a direct sum of subspaces let me not use K, let me use something else. Let's say R, where each of them, all of these Wi's are A invariant. Yeah, in that case, if this is basis B1, this is basis B2, and this is basis BR, then we can have a basis B, which is B1 union B2 dot 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 union BR for the whole space V. And in this basis, the operator is going to look like A11, A22 dot 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 up to ARR, all big zeros here, where of course AII is of size F di cross di, where di is nothing but the dimension of the subspace Wi. This is the decomposition theorem. So all we need is a direct sum decomposition of V into A invariant subspaces. Direct sum decomposition of V into A invariant subspaces. Yeah, one might also add smallest possible A invariant subspaces. Yeah, because we want a block diagonalization beyond which we cannot diagonalize any further. Right? That's the best possible thing that we can do beyond diagonalization. So all those matrices or all those linear operators which are not diagonalizable, for them we can try and decompose the whole space into such A invariant, smallest possible A invariant subspaces, so that the whole space can be written as a direct sum of these subspaces. In that case, the linear operator represented in terms of the basis obtained from these A invariant subspaces, smallest possible A invariant subspaces, will have the structure of a block diagonal matrix which can not be further decomposed. Right? Now the question is, how do we get these subspaces, these A invariant subspaces? So how to get this direct sum decomposition? That will be the subject matter of the next module, right? But before we go to the next module, I want you to do this following homework or immediate attention problems. Namely, for the same exercise, yeah. So for the situation, if I write V as W prime plus W instead of W plus W prime, where this guy is A invariant, but I don't know whether this guy is, there's this unknown. It's maybe A invariant, may not be A invariant. And so I have my basis given by B prime union B. Now see, it's an ordered basis. All these things require ordering of the basis vectors. So if I order them differently, I take vectors from W prime first and then I take vectors from W. In that case, how A is going to look like in this basis. So find out A in this basis. Yeah, that is your immediate attention problem 1. Immediate attention problem 2 would be find out all possible invariant subspaces for these matrices. So suppose I have a matrix A, which is, say, diagonal matrix 1, 2, 3, 4. Yeah. For this, find out all A invariant subspaces. Find out all possible A invariant subspaces. Repeat for A equal to, say, 1, 2, 3, 4. But there is a 1 here, 1 here, 1 here. Repeat for A equal to 1, 1, 0, 1, 0, 1, 1, 0, 1, then 2, 1, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. Right? Do these problems and let's meet on the other side of the break. Okay.